We're given the vector field f and asked to find a function little f so that the vector field f equals the gradient of f. Because we're told to find the function little f, which is called a potential function, we can assume that the vector field f must be conservative, otherwise we would not be able to find the potential function little f. Let's begin by verifying the vector field is conservative by performing the test for a conservative vector field in 3D shown here below, where the vector field f has components p, q, r, where each component has a continuous partial derivative over an open region R, then the vector field f is conservative if and only if these partial derivatives are equal to each other. Well, notice in our case, p is equal to 3yz, q is equal to 3xz plus 2, and r is equal to 3xy plus 2z. Now let's begin checking the partial derivatives. Let's first find the partial of r with respect to y, which is a derivative of 3xy plus 2z with respect to y. So we'd have 3x plus 0 or 3x. And this must be equal to the partial of q with respect to z, which is a derivative of 3xz plus 2 with respect to z, which would be 3x plus 0 or 3x. So these two partials are equal to each other. And now let's check these two. So we have the partial of r with respect to x, which is equal to the derivative of 3xy plus 2z with respect to x, which would be 3y plus 0 or 3y. This must be equal to the partial of p with respect to z, which should be the derivative of 3xyz with respect to z, which would be 3y. So these two are also equal. And now we need to check these two last partial derivatives. So we have the partial of q with respect to x, which is the derivative of 3xz plus 2 with respect to x, which would be 3z plus 0 or 3z. And finally we have the partial of p with respect to y, which would be equal to the derivative of 3yz with respect to y, which is also 3z. So this does confirm the vector field f is conservative. Now let's work on determining the potential function little f of x, y, z. Again, we now know that the vector field is conservative, so our goal is to find the function little f of x, y, z such that the vector field f equals the gradient of little f. Remember, the gradient of f would have components: the partial of f with respect to x, the partial of f with respect to y, the partial of f with respect to z. Which means 3yz must be equal to the partial of f with respect to x, 3xz plus 2 must be equal to the partial of f with respect to y, and finally 3xy plus 2z must be equal to the partial of f with respect to z. Which means to reconstruct or determine the function little f of x, y, z, we integrate, and we'll integrate the x component with respect to x, the y component with respect to y, and the z component with respect to z. So this first integral would be the integral of 3yz integrated with respect to x. This integral here would be the integral of 3xz plus 2 integrated with respect to y. And here we'd have the integral of 3xy plus 2z integrated with respect to z. So by determining these three antiderivatives, we should be able to analyze them and reconstruct the potential function little f of x, y, z. So here, we integrate with respect to x, treating y and z as a constant. So we would just have 3xyz. Now this antiderivative is only recovering the x part, so we could be missing y terms and z terms, yz terms, and a constant. So let's write this as plus a function of y and z. Let's call it j of y, z. Next, we integrate with respect to y, treating x and z as constants. So we'd have 3xz times y, or 3xyz, plus 2y. Now here we could be missing x terms, z terms, and xz terms. So we're missing a function of x and z as well as a constant. So let's write plus k of xz. And then for our third integral, we integrate with respect to z, treating x and y as constants. So the antiderivative of 3xy with respect to z would be 3xyz plus the antiderivative of 2z with respect to z would be 2 times z squared divided by 2, which would be z squared. Here we could be missing x terms, y terms, and xy terms, as well as a constant. So let's write this as a function of xy as L of x comma y. And now by analyzing these antiderivatives, we should be able to reconstruct f of x comma y comma z. Notice all three antiderivatives have the term 3xyz, which would be part of little f. The second antiderivative has the term 2y, which must also be a term in little f. And finally, the third antiderivative has the term z squared, which must also be a part of little f. So we have plus z squared, and then plus k for the constant of integration. So this is the function little f that we're looking for, which will help us evaluate the line integral based upon the fundamental theorem of line integrals. So going back to our first slide, we now know that little f is equal to 3xyz plus 2y plus z squared, and notice how the constant of integration is already here. So now we want to use this potential function to evaluate the line integral along the curve C of f dot differential r, where the curve C is defined here. Before we do this, let's review the fundamental theorem of line integrals. If C is a piecewise smooth curve lying in an open region R, given by the vector function r of t, if the vector field f is continuous and conservative, then the line integral along the curve C of f dot differential r is equal to little f of x of b, comma y of b, comma z of b, minus little f of x of a, comma y of a, comma z of a, where the function little f is the potential function of the vector field f, which we already found. So because we know the vector field f is conservative, and we found the potential function to be little f of x comma y comma z, we can now use this to evaluate this line integral. Before we do this, you'll notice how x of t is equal to t squared, y of t equals t plus 3, and z of t equals 2t minus 3. And the interval for t is a closed interval from 0 to 2. So using the fundamental theorem of line integrals, this line integral equals little f of x of 2, comma y of 2, comma z of 2, minus little f of x of 0, comma y of 0, comma z of 0. So x of 2 is equal to 2 squared, which equals 4. Y of 2 is equal to 2 plus 3, which equals 5. And z of 2 is equal to 2 times 2 minus 3, which equals 1. And x of 0 is equal to 0 squared, which equals 0. Y of 0 is equal to 0 plus 3, which equals 3. And z of 0 is equal to 2 times 0 minus 3, which equals negative 3. So here we have f of 4, comma 5, comma 1 minus f of 0, comma 3, comma negative 3. So performing substitution into f of 4, comma 5, comma 1 would be 3 times 4 times 5 times 1 plus 2 times 5 plus 1 squared. And f of 0, comma 3, comma negative 3 would be 3 times 0 times 3 times negative 3 plus 2 times 3 plus negative 3 squared. So simplifying, we get 60 plus 10 plus 1 minus 6 plus 9, which equals 71 minus 15, which equals 56. So this is the value of the line integral using the fundamental theorem of line integrals. I hope you found this helpful.